Hi, today I'm going to talk about our project Iterative Teaching by Data Hallucination. Consider a span filter, which is a simple machine learning system, which has a threshold, and this threshold will get adjusted according to the legitimate content over time. Let's say we have an adversarial attacker. If this attacker has access to the span filter and also the algorithm and also the status of the span filter, then this attacker can basically send specially designed emails to the span filter to influence the threshold. This is called training set poisoning and is a very classical example of machine teaching. So in machine teaching, what we have is we have a learner, which could be a randomly initialized neural network, and we have a teacher, which can be anything. And the teacher has access to some W star. And the teacher can influence the students by providing example pairs. And the goal of the teacher is to let the student to converge to this target concept, to this W star, as fast as possible. Here you can see our framework. Our framework is based on the iterative machine teaching, where a teacher performs example selection. We, on the other hand, we propose to use a generative model or to try to solve an optimization problem to model this teaching process. The difference to the normal generative model is that we have a different objective. We are trying to facilitate the convergence of the student. And also the data distribution we are trying to model is also changing dynamically depending on the learner status. We have identified some limitations of previous IMT-based methods. First of all, the teacher has a very limited modeling flexibility. The performance is bounded by the dataset. Also, it's very inefficient. It has to go through the complete dataset at each iteration, making it very difficult to scale to very large dataset. Also, it assumes to know W star and cannot handle black box teaching of neural learners. To formalize a problem setting, the teacher has access to all kinds of information of the learner. For example, the model parameter, the learning rate, the loss function, or the optimization algorithm, and can only influence the students by providing sample pairs. The teacher objective is to minimize the distance between WT and W star. WT is the student's model parameter after T iterations. And the student is considered to be passive and can only perform optimization after receiving the data. Here's an overview of our method. We differentiate between Omniscient DHT and black box DHT. The difference is that in the Omniscient setting, the target model parameter W star is known, while in the black box setting, we don't have W star. We are trying to optimize something else. So in the Omniscient DHT, the most natural idea would be to perform some kind of greedy teaching policy. So we are trying to perform one-step optimization to optimize for the optimal sample X conditioned on the uniformly sampled label Y. More formally, we are trying to solve this optimization problem at each iteration. There are some problems of this greedy teaching policy. First of all, it's of course suboptimal because we are only considering one-step updates for the learner. It's computationally very expensive if X is high-dimensional, for example, for images. And we are not considering any data distribution constraints, making it often not interpretable for humans. But still, we can see here that compared to the baseline method, for example, SGD, which is basically you don't have a teacher, or IMT, we can still outperform these baseline methods by a great margin. So we are trying to improve upon this greedy teaching policy. We propose a parameterized teaching policy. So the basic idea is to parameterize the teacher by a neural network. And the teacher basically take as input the data label pair, the current status of the student model, and the W star, and tries to learn a nonlinear mapping between ground truth data to some ground truth data to some x tilde, and basically is trying to solve this nested optimization problem. We solve this problem by performing algorithm unrolling and by propagating through the whole objective to update our teacher model. Still, we don't have any guarantees on the data distribution. Here you can see the result. So we can see the convergence behavior is even better than before, than the greedy setting. But clearly we can also see that the data is outside of the data distribution. For example, for the images, we can only notice some noise. It's not very interpretable for human what is actually happening here. So we are trying to impose some additional constraint, distribution divergence constraint. So we want the difference between the original data distribution and the generated data distribution to be within some epsilon neighborhood. And we have two different formulations based on two different generative models. The first formulation is GAN-based. So we are directly trying to teach in the image space, and the teacher will act as a generator. And we have an additional discriminator to try to enforce that we are generating realistic samples. And the other formulation is based on VAE. So here we are teaching in the latent space. So we utilize a pre-trained VAE, which already captures the data distribution. And we can recover the data using this pre-trained decoder. And the teacher only has to kind of modify the latent space, and then we can have different kind of data. Here you can see the results. So we can see that the VAE-based teacher can generate samples that are identifiable for us human. But here we are performing 3 and 5 binary classification, and we can see that it still outperforms SGD. But it also comes as cause of the convergence behavior. Because we have this very limited teaching space, it's only the latent space. Where in the GAN-based teacher, we can actually outperform the other baseline method. Actually, what is very interesting here is that you can see that the teacher learns implicitly a denoising process. So at the beginning, it sends out these very noisy images, which could contain much information about the model weight, and the model converges very fast. But then it gradually denoises the images, and it becomes some kind of a fine-tuning process. In practice, sometimes we want the opposite. So we want generated samples to be semantically very distinct from the original data distribution. This could be beneficial, for example, in the medical domain, where we don't want to leak sensitive information about the patient. So in this case, we are basically trying to generate samples that are at least some epsilon neighborhood away from some privacy step in the latent space. Here we show that it is possible and still able to achieve very good convergence behavior. So now we come to the black box DHT. First of all, the black box teaching of neural network has been an open challenge in iterative machine teaching. The goal is now different, so we are now trying to improve the learner's generalization instead of the convergence, because we don't have W star. It has many challenges. For example, without this very strong signal W star, it is very difficult. It's also very unclear how to really encode very deep neural networks to some kind of embeddings to kind of decode the data. It's also very difficult to generate plausible samples. Here we take usage of some surrogate for W star from the underlying joint data and label distribution, which is basically the validation accuracy. So the major intuition here is we want to reduce the teaching space. We want to simplify this problem. So how much can we reduce it? We can actually reduce it to one single hyperparameter. We take inspiration from neural architecture search and mix up data augmentation. And basically, we are trying to predict this interpolation coefficient. And based on some signals of the current pseudo model weight. And we have here two different variants. We can either learn optimize the teacher using algorithm unrolling or using policy gradient to train the teacher model. Another type of black box DHT is called performative teaching. So in performative teaching, we take the inspiration from performative prediction, which has the idea that the model prediction should influence the data distribution sometimes. So our idea is instead of teaching the whole very deep neural network, we are dividing it into two parts. So we have a neural encoder, and we have a linear classifier layer for most of the classification models. And we are basically teaching in this latent space. So what we are doing is we are trying to perturb the feature in certain direction, such that this perturbation will result in a gradient that will update the whole neural network. And we can basically guide the direction of this perturbation. And we guide it in such a way that is still epsilon away from the original feature. And we are also only optimizing along a hypersphere. And the direction is determined by some local W star. This local W star is obtained by locally optimizing this linear classifier for several steps. Pretty similar to something like a look-ahead optimization. And after performing this this kind of teaching, we can actually achieve better generalization. So here you can see the results of our DHT teaching. We can see it can outperform SGD with no teacher or random policy. So random policy is we are still performing this kind of perturbation, but in random direction, so no guidance from the teacher. And we can see that you really have to have this additional knowledge from the teacher to really improve the generalization of the pseudo model. On the right, we can also see our mix-up based teacher, which also improves the generalization of the model. So in summary, we propose a novel teaching framework. We call it data hallucination teaching, where the teacher iteratively generates synthetic data depending on the learner's status. DHT has a great advantage that it has a very flexible teaching space. In DHT, we comprehensively study the teaching policies under both the Omniscient and the black box scenarios. We propose a very normal performative formulation for iterative teaching, which assumes a dynamically changing teaching target. The formulation is shown to be a natural fit for teaching black box neural learners. And for the first time, we are able to apply this iterative teaching to black box neural learners on realistic datasets with significant performance gain. We demonstrate faster convergence of DHT versus other teaching baselines and non-teaching baselines, both theoretically and empirically. Thank you very much.